you ever thought about the worlds we don't talk about? Not the giants with rings or the red deserts that steal the headlines, but the quieter ones, the dim and distant shapes that orbit in the cold beyond Neptune. They move slowly, almost forgotten, yet they hold the record of how the solar system grew. Their paths are clues, their surfaces time capsules. To study them is to read the margins of a cosmic story we thought we already knew. If you enjoy this kind of quiet exploration, a simple like and subscribe helps others find their way here too. Settle in. Let's turn toward the outer edge, where the forgotten planets wait in the dark. Out beyond Neptune, sunlight thins to a gray glow, and the heat falls away. Yet the solar system keeps going. It stretches for billions of kilometers into a wide, cold zone, filled with small, icy bodies. These are the forgotten planets, worlds that formed from the same disk of gas and dust as the big planets, but never grew large. Many are round, some are irregular. They move slowly, and the light they reflect is faint, like winter moonlight. For a long time, they escaped attention because they were dim and distant. When they were finally noticed, their status shifted as astronomers learned more, and many were grouped as minor bodies. Still, they hold records of how our neighborhood came to be. They are timekeepers in ice and stone. Their orbits are long and stretched, like elastic pulled wide and let go in slow motion. A few carry thin atmospheres. Some have tiny moons. Some even show signs of internal heat that reshapes their surfaces over long spans of time. Step by step, we can read them as we would read fossils, not for drama, but for the patient clues they offer. Following those clues will take us from the inner debris of the asteroid belt to the dim edge beyond Pluto, tracing how these small worlds formed, what they preserve, and how their quiet details change our picture of the solar system. Between Mars and Jupiter lies a broad ring of rock and dust. In that ring, one world stands out. It is small and subdued, but it once carried the title of planet. This is Ceres, the largest object in the asteroid belt, and the only dwarf planet in the inner solar system. While the major planets shine and spin with confidence, Ceres turns without show, holding its course like a note in the background. Ceres was first observed on the first night of a new century, the 1st of January, 1801. The Italian astronomer Giuseppe Piazzi was charting stars when he noticed a point of light that moved slightly from night to night. The motion was steady and slow. It looked like a planet, and for a time it was taught as one. Textbooks placed Ceres between Mars and Jupiter, and the idea made sense until more small bodies were found in the same region. Pallas, Juno, Vesta, and many others followed. As the count rose, Ceres looked less like a single planet and more like the largest member of a crowded zone. By the mid-1800s, it was listed as an asteroid, and its name faded from common memory. Yet Ceres is not a typical asteroid. It holds nearly a third of the mass of the entire belt. If the belt were a country, Ceres would be the quiet capital. Its surface is a little brighter than most of its neighbors, and that brightness points to a key ingredient: water ice. Evidence suggests that Ceres holds a large amount of water locked in its crust, mixed with rock and salts. Some studies indicate that briny liquid, very salty water may still exist below the surface. That makes Ceres different from dry, rocky fragments. It is a mixed world, with both stone and ice. When NASA's Dawn spacecraft arrived in 2015, it mapped Ceres up close and saw something striking in a crater named Ocata, bright white patches that stood out against the darker ground. These spots reflected light, like fresh frost. Analysis showed they were deposits of sodium carbonate, a kind of salt left behind when briny water rose from below, froze, and then sublimated, which means it turned from ice to vapor and left the salt behind. The bright deposits are direct hints of internal activity. They mark places where the inside of Ceres reached the surface. Ceres may also host cryovolcanism. A cryovolcano is a cold volcano that releases water-rich slurries instead of molten rock. The best example on Ceres is Ahuna Mons, a solitary mountain with smooth flanks that rises above the plains. Its shape and lack of heavy cratering suggest it formed relatively recently, in geologic terms perhaps hundreds of millions of years ago rather than billions. That time frame is still extremely long compared to human history, but it tells us that Ceres has not been completely dormant. Materials have moved from inside to outside in the recent past, driven by slow heat and the behavior of salty ice. A day on Ceres is simple and quiet. Sunlight is weak, and shadows stretch far. Temperatures stay well below freezing. There is no thick atmosphere to blur the view, so starlight stays steady and sharp. With almost no air, there is no wind to lift dust and no sound to carry. Impacts by tiny grains still happen, ticking away at the surface over time, but even those happen in the slow, thin hush of space. The gravity is gentle, about 3% of Earth's, so a step would feel like a soft leap, and a dropped pebble would fall in slow motion. Nothing hurries. Ceres sits between two broad families of worlds. Inside its orbit, rocky planets are built from metal and stone. Outside, the giants hold thick envelopes of hydrogen, helium, and ices. Ceres seems to be a leftover building block, what scientists call a planetesimal, a body that formed early and could have grown larger if conditions had allowed. If Jupiter had not formed so quickly and with such mass, Ceres might have gathered more material and become a true planet. Instead, it stayed small, preserved by its position and by the large planet nearby, which stirred the belt and kept big growth from happening. This halfway state makes Ceres valuable for study. It samples the ingredients that once filled the inner solar system and helped form Earth. Those ingredients include water, salts, and carbon-bearing compounds. Because Ceres and objects like it carry water ice, they are part of the long story of how Earth's surface became wet. Many models suggest that early impacts by small bodies delivered a share of the water that filled our oceans. In that view, Ceres and similar worlds are not just background debris, they are couriers. They show what was available to be delivered and how those materials behave over time in small, cold worlds. Learning about them helps us connect the chemistry of early space with the environment where life later took hold. Ceres circles the Sun in about 4.5 years. The orbit is calm and regular, sitting in that broad gap between Mars and Jupiter. It does not blaze or surge. It keeps its time. If you stood on its surface with a clear view to space, the Sun would look like a bright disk, but not an overwhelming one, more distant than you are used to. Earth would be a small blue point far away, easy to miss if you were not looking for it. With no air to carry sound, the only steady noise would be your own breath and the hum of your suit. The horizon would curve gently underfoot. Above you, space would be deep and clean. In that setting, Ceres does not feel like a failed world. It feels like a preserved one. It holds a record of the early solar system and shows what can happen inside a small, icy rocky body over billions of years. It has seen the big planets form and settle. It has shared the sky with passing comets, and with the steady traffic of smaller asteroids. Through all of that, it kept turning, slowly changing in ways that careful instruments can still read. It sits halfway between the inner rock and the outer giants, easy to overlook, steady in its place, forgotten by most, but never gone. Far beyond Neptune, in the Kuiper Belt's dim reach, a world turns that seems pulled along by its own motion. Haumea is not a neat sphere. It is stretched, with a shape closer to a rugby ball than a globe, because it spins at an extreme rate. One full turn takes about 4 hours. That pace makes it the fastest rotating large body known in the solar system. For comparison, Earth takes 24 hours to rotate. Haumea spins roughly 6 times in that span. On a surface like that, the horizon would appear to slide by more quickly than your eyes expect. At the equator, you would feel slightly lighter than near the poles, because rapid spin pushes outward, a gentle effect called centrifugal force. This spin is a main reason the body looks flattened and elongated instead of round. Many scientists trace that speed to a major impact long ago. Early in solar system history, collisions were common. Ice rock worlds struck one another at high speed, merging, shattering, or glancing off. A strike off center can add spin, and a strong one can add a lot. In Haumea's case, a glancing blow may have set the body rotating so fast that it stretched, and the same event may have thrown off debris that never escaped. Some of that debris likely became companions. 2 small moons circle Haumea. They are named Hiyaka and Namaka, after figures from Hawaiian tradition that also gave Haumea its name. Each moon is tiny next to the main body. Their orbits are a bit tilted relative to Haumea's equator and to one another, and over years they shift in a slow dance set by gravity. The pair keep steady company as their parent world moves through the dark. Their behavior helps researchers measure Haumea's mass and refine its shape, because small changes in the moon's paths record the pull of the world beneath them. Haumea also has rings. They are thin, narrow bands, about 1,000 kilometers above the surface. Only a few bodies outside the giant planets are known to carry rings, so finding them here was surprising. The ring particles are likely ice and rock chips from the ancient impact, or from later episodes where small pieces were shed. In the weak sunlight, the ring would not blaze like Saturn's. It would be a dark, fine trace that still carries clear information for anyone measuring how light dims when the ring passes in front of a distant star. Events like that, called stellar occultations, are one of the main ways the rings were confirmed and described. The surface of Haumea adds another clue. It reflects a lot of light, more than most objects at this distance. Measurements of its spectrum, the way it reflects different wavelengths, show the mark of crystalline water ice. Crystalline here means the water ice molecules are arranged in a regular pattern, like a mineral lattice, instead of being amorphous, which is more disordered. In the outer solar system, radiation from space tends to damage crystal patterns over time, so seeing a clear crystalline signal suggests the surface has been renewed. Renewal could come from small impacts that expose fresher ice, from grains being ground and refrozen as the body spins, or from small amounts of material rising from within. However it happens, the surface looks young compared to its true age. Inside, Haumea seems to be a mix of rock and ice. Its overall density is higher than pure ice, pointing to a rocky core wrapped in an icy mantle. Some models allow for layers and pockets where salts could lower the melting point and let tiny amounts of liquid persist for a time. At this distance, heat is limited, so any liquid would be local and temporary, not a global ocean. Still, even a little internal warmth can help reshuffle the surface over long periods. In a system that changes slowly, small effects matter when you give them millions of years. The sun here is dim. Light takes nearly 6 hours to travel outward to Haumea when it is near its average distance. That means everything runs on a quiet clock. Yet the body refuses to match that pace. It spins at its own fast rhythm. This difference is part of what draws attention. Big planets usually settle into shapes close to spheres because gravity pulls evenly in all directions. Haumea is a case that breaks that pattern, holding a stretched form because rotation reshapes the balance. Its elongated figure and speed make it an outlier among worlds of its size. Haumea orbits far beyond Neptune, taking about 284 Earth years to complete one loop around the Sunday. It spends that time in the Kuiper Belt, a broad zone filled with icy remnants from the time when planets were forming. Many bodies out there are dark and small. Haumea stands out because of its size, its reflective ice, its rapid spin, its ring, and its moons. In width, along its longest axis, it rivals Pluto, though it is less massive. The combination of features gives it a distinct signature against the belt's backdrop. Imagine the surface. Gravity is weak, roughly a tenth of Earth's, so each step would have a slow bounce. Because the world is elongated, the ground would fall away more steeply along the short axis than along the long one. The geometry would feel slightly unfamiliar. The sun would trace a fast path in the sky every 4 hours, a bright point rather than a wide disk. Long, sharp-edged shadows would sweep across ice-coated ground. The 2 small moons would shift their positions noticeably over a single day. No wind would carry sound. The only steady noise would be inside your suit. In that setting, the steady, rapid spin would be the most certain motion, a constant you could set a clock by. Haumea's presence is a reminder that the solar system still holds many forms. Not every world settles into quiet balance. Some keep moving at the edge of what their structure can allow, and over time, they show how shape, spin, and composition interact. A ring 1,000 kilometers above the surface is not decoration. It is a record of past events and current forces traced in dust and ice. 2 moons are not just ornaments. They are instruments that tell us mass and distribution. A bright, icy spectrum is not a shine for its own sake. It marks a surface that has been stirred or renewed. Each piece of data adds to a plain picture that still feels rare. A large, icy body that spins fast, stays stretched, and carries its own small system with it. Farther along the belt, another dwarf planet drifts with a different style. Makemake is smaller than Pluto, about 2/3 its diameter, and carries a soft red tint. Where Haumea flashes bright with clean water ice, Makemake reflects less light and shows a color shaped by chemistry at very low temperatures. It was discovered in 2005, around the Easter season, and it was named for a creator figure from the culture of Rapa Nui, Easter Island. The pronunciation is simple and steady. Make, make. Most objects in the Kuiper Belt are dark, because their surfaces have been altered by radiation for a very long time. Makemake's reddish tone comes from that process. The surface holds frozen gases, such as methane and nitrogen. In this cold, gases can freeze into solid frost. Over long spans, ultraviolet light from the sun and cosmic rays, high-energy particles from space change simple molecules like methane into more complex ones. The result is a mix of dark, carbon-rich compounds called tholins. Tholins are not living material, but they are organic in the chemical sense. They contain carbon, hydrogen, and often nitrogen. They are interesting because they are a step on the path from simple molecules toward the complex chemistry that life uses. On Makemake, tholins coat the frost and tint the ground a rusty red. The color is not uniform. Patches may be darker or lighter depending on how much fresh ice is exposed and how long a region has been left undisturbed. The temperature is around 200 degrees Celsius, about 70 K. At those values, water is rock hard. Methane and nitrogen are mostly frozen, and change is slow. That slow rate is how the surface can hold a long record. Each grain of frost is like a page where radiation has written a mark. Over time, small impacts or seasonal changes can expose new material, resetting the clock in places. Makemake likely has a very thin, changing atmosphere. Thin here means the pressure would be near vacuum compared to Earth, more like a trace than a true sky. When Makemake is at the closer part of its stretched orbit, sunlight is a little stronger. Frozen methane and nitrogen can sublimate, go directly from solid to gas, and form a faint, temporary envelope. Later, as the world moves farther away and cools, the gas settles back as frost. This on-again, off-again atmosphere is expected for bodies with volatile ices. Volatile means they change phase easily in cold outer orbits. It is hard to detect, but when it appears, it tells scientists about surface temperatures and the balance between sunlight and escape to space. In 2016, a small moon was found close to Makemake. For now, it is nicknamed MK2. It orbits within the glare of the main body and is easy to miss, which is why it was overlooked in earlier observations. A moon is valuable because its orbit can be used to measure Makemake's mass. With mass and size together, scientists can estimate density, which reveals the ice-to-rock ratio. That ratio helps place Makemake among its neighbors. Some dwarf planets are icier, some are rockier. Even a tiny companion, only a couple of 100 kilometers wide, can answer large questions about the parent world. Makemake goes around the Sun in about 305 Earth years. It lives, like Haumea, in the Kuiper Belt, though not in the same orbit. The light travel time from the Sun is more than 7 hours when it is near its average distance. Out there, the Sun looks like a bright star. Without a thick atmosphere, the stars keep their hard points of light and do not shimmer. Day and night are not busy with weather. They are quiet times with long shadows and slow change. On the surface, gravity would be about 7% of Earth's. If you walked in a suit, your steps would lift you a little more than you expect, and you would come down slowly. The ground would be dark red to brown in many places, with sparkles where frost grains catch the light. The texture would be like compacted snow or very fine frozen dust. The air, or rather the near vacuum, would carry no sound. Your shadow would fall sharply, and it would stretch far when the sun is low. Time would feel slower because fewer things happen quickly. Yet even here, chemistry would keep working, small changes adding up over long spans. Makemake's discovery came with others, Eris, Haumea, and more, that showed the outer solar system is crowded with dwarf planets and large Kuiper Belt objects. Those finds pushed astronomers to refine the definition of a planet and helped move Pluto into the dwarf planet group. Makemake is one of the 5 officially recognized dwarf planets today. Its presence does not reduce the system, it extends it. The map beyond Neptune is not empty. It is full of quiet bodies that preserve early conditions. What makes Makemake stand out is its plainness that still informs. It does not have deep bands and storms like Jupiter. It does not have wide, bright rings like Saturn. It does not have the fast spin and stretched figure of Haumea. Instead, it shows how basic ingredients, methane, nitrogen, simple ices behave when they sit for eons in cold light. The tholins that grow from that setting are simple products with complex importance. They remind us that carbon chemistry starts even where heat is scarce. The name fits. In Rapa Nui tradition, Makemake is a creator. Linking that idea with a small, distant world is not about making poetry. It is a direct nod to the idea that early ices and organics are the raw materials from which later things are built. A dwarf planet like this can carry those materials safely for billions of years. When pieces break off, or when similar bodies strike young planets, they can deliver samples to warmer zones where water is liquid and reactions run faster. In that way, small worlds help connect the cold storehouses of the outer system with the places where surface oceans and air later formed. Makemake is a reminder that quiet objects can hold clear records. There is no need for noise to make a point. A dim red globe moving on a long path can tell us how sunlight, radiation, and time can change simple ices. It can show how a thin, seasonal atmosphere works at the edge of space. It can anchor a mass and density that tie into models of formation. It can carry a moon that turns a faint speck into a measuring tool. None of that requires drama. It requires patience and careful light. Seen that way, the Kuiper Belt is not background. It is an archive. Each dwarf planet is a file that has not been thrown away. Each reflects a slightly different mix of rock and ice, a different history of heating and cooling, a different level of exposure and renewal. Haumea is fast and bright, stretched and ringed. Makemake is steady and red, frosted and slow to change. Both extend the story that began near the sun into a zone where time lengthens and the rules are the same but the pace is different. Makemake glides on through the Kuiper Belt, red and silent, spinning slowly beneath the sharp stars, carrying the memory of the solar system's first days across the dark. Far outside Neptune, where the sun is small and the stars keep sharp edges, a distant body forced us to redraw the map in our heads. Its name is Eris. It is a little smaller than Pluto in size, yet heavier, denser, colder, and harder to ignore. When astronomers first measured it, the quiet world set off a loud argument on Earth. The year was 2005. A team led by Mike Brown at Palomar Observatory spotted a bright point far beyond Neptune and tracked it across the sky. Early estimates suggested a world that could rival Pluto. For decades, Pluto had been the odd outer member of the family. Now there was another object of similar scale, maybe even larger. Old questions, long parked in footnotes, moved to the front. What exactly makes a planet a planet? If Pluto qualifies, does this new body qualify too? If both count, which others should we add? In 2006, the International Astronomical Union voted on a definition. To be a planet, an object must orbit the Sun, be round under its own gravity, and clear its orbit of other debris. Pluto and Eris passed the first 2 tests, but not the third. They share their space with many icy neighbors. The new category, dwarf planet, was created, and both were placed there. The choice upset many people. Pluto had fans, and schoolroom memories are strong. Eris, new, cold, and blameless, was dubbed by some the planet that killed Pluto. Jokes and headlines spread. Letters arrived. For a time, a nickname linked Eris with the Queen of the Underworld. The official name, Eris, matched the moment. In Greek myth, she is the goddess of strife and discord. Eris itself does none of that. It is a frozen world, about 2,320 kilometers across, just under Pluto's diameter, but with more rock mixed into its ice. That makes it roughly 27% more massive than Pluto. Eris orbits the Sun at an average distance of more than 10 billion kilometers and needs about 557 years to complete one loop. At its farthest, it is nearly 3 times beyond Pluto's greatest distance. Light from the Sun takes close to 9 hours to get there. The warmth is so faint that the surface stays near 230 degrees Celsius. Most of the ground is thought to be nitrogen ice with patches of frozen methane, both bright in weak sunlight. Through a telescope, Eris looks like a steady, cold pin of light, small, clean, and reflective against the black. A small moon circles it. The moon is called Dysnomia, the mythic daughter of Eris, and a name linked with lawlessness. Dysnomia is around 350 kilometers wide and orbits at roughly 37,000 kilometers. By tracking the moon's path, astronomers measured Eris's mass and confirmed that this dwarf planet outweighs Pluto even though it is slightly smaller in size. The pair drift together like a quiet system in the far dark. Picture the scene up close. The Sun is a hard white star. The sky is black at noon, and the ground is pale, crisp, and strong underfoot. Gravity is gentle, about 8% of Earth's, so each step is a careful bound. There is no breeze and no sound, only your breath and the soft creak of your suit. Time feels paused. Yet, by simply existing, Eris changed our labels. It showed that names and lists are tools we use. The universe does not use them. Eris did not aim to push Pluto aside. It moved on its path for billions of years until our instruments were good enough to see it. The choice of names suits the story. Eris stirred debate without lifting a finger. Imagine coasting in deep space for eons, and the moment you are noticed, you start an argument among humans. Far inside the warmth of the Sunday, with distance, the mood has shifted. Astronomers now see Eris as a key sample from a specific region, the scattered disk. The scattered disk lies beyond the Kuiper belt and holds objects on stretched, tilted paths. Long ago, Neptune's gravity likely flung many of them outward. Some may have been nudged by passing stars when the Sun was young. Eris belongs to this group. By studying its orbit and makeup, researchers pieced together how the outer system was shaped, why some bodies stayed near Neptune while others were thrown far away. The lesson is simple and firm. Size alone is not the story. Many objects circle in the dark, most too small to have names yet, and they are part of the same system that includes Earth and Jupiter. Eris is the one that made us look again and admit that the tidy list of 9 was never the full picture. Follow the map even farther, and another kind of distance appears. Past the Kuiper belt and the scattered disk, where the Sun's pull is thin and patient, a red body moves so slowly that a human life is less than a blink to it. This object is Sedna. It is one of the most remote known members of the Sun's family. While the planets finish orbits in years, Sedna takes about 11,400 Earth years to go around once. Whole languages could rise, spread, and fade before Sedna completes a single lap. Sedna was discovered in 2003 by a team that also included Mike Brown. What shocked observers was not its size. It is smaller than Pluto, but its path. Even at its closest, Sedna stays about 76 astronomical units from the Sun. An astronomical unit, or AU, is the average Earth-Sun distance. Neptune orbits at about 30 AU. At its farthest, Sedna reaches more than 900 AU, nearly 100 times Earth's distance. From there, the Sun is a bright point, not a disk. This extreme orbit does not match the flat, tight ring of the Kuiper belt. Instead, it hints at a different zone, the inner edge of the hypothesized Oort cloud. The Oort cloud is an idea supported by many clues. It would be a vast, spherical shell of icy bodies that surrounds the solar system like a thin halo. If Sedna belongs to that inner region, then it is a first, a lone messenger from a place we have never visited and can barely measure. Its surface is dark red, among the reddest in the solar system. The color likely comes from Tholin's complex organic compounds that form when ultraviolet light and cosmic rays strike simple ices like methane and nitrogen. Over great time, radiation breaks and rebuilds molecules, making a tar-like, carbon-rich film. On Sedna, this process could have run almost undisturbed for billions of years, deepening the red. The tone is not fresh paint, it is the color of age. Temperatures near Sedna fall to around 240 degrees Celsius. Nitrogen and methane, common gases on Earth, are rock-hard solids here. Any thin atmosphere that might appear near its closest approach would soon freeze back to the ground as frost. With no real air, stars do not twinkle. They stand sharp and still. The silence is complete. The sunlight arrives as a whisper. If you stood on Sedna, the sun would look like a bright star. Shadows would be razor clear, cast across a plane that glows faintly under weak light. Gravity would be about 5% of Earth's. Steps would feel like slow-motion hops. The sky would not move much. Day and night would pass in long, low-contrast stretches that feel like twilight. How did Sedna reach such a path? Several ideas compete. One is that a star once passed near the young solar system. Even a distant pass can tug on small bodies, lengthening and tilting their orbits. Another idea is that a yet unseen giant, sometimes called Planet 9, shaped the far region and nudged Sedna into its present track. A third possibility is that Sedna formed far out from the start, in the zone where the sun's gravity is weak, and it has simply been circling ever since. Whatever the cause, Sedna behaves like a time capsule. It is probably geologically quiet. There are no signs of active volcanoes or global seas. Its surface records a very long story of slow radiation damage, faint heating, and occasional impacts. Each crater and ridge is a mark that may go back to the early days when planets were still assembling. The timescale is hard to grasp. Earth orbits in 365 days. Pluto needs 248 years. Sedna needs 11,400 years. When Sedna last came closest to the sun, mammoths roamed, and human cave art was young. By the time it returns again, our species, our cities, and even our coastlines may be very different. Compared to Sedna, the fastest changes on Earth are brief flashes. Its pace makes it feel almost outside the solar system, a member by law, but a stranger by habit. It circles the sun, but so slowly. That motion is a measure for historians, not for calendars. That is the point. The solar system is not a neat set of rings laid out like tracks on a field. It is orderly near the sun and messy at the edge. The outer parts are stretched. Objects live on orbits so wide that sunlight takes hours to arrive and energy is sparse. They do not show up in the evening sky. They live in the system's memory. These are remnants of how things began, preserved because nothing has warmed them enough to erase their first states. Sedna is one of those remnants. It changes little, and that is useful. It is a stable ember, glowing dull red under distant light, carrying a record of chemistry and weathering that runs almost the length of solar system history. Eris and Sedna together mark two faces of the far zone. Eris is bright, heavy for its size, and linked to the scattered disk, where Neptune's pull once sent bodies flying. Sedna is dimmer, redder, slower, and sits on a path that reaches toward the Oort cloud, where the sun's rule fades and the galaxy's tides begin to matter. Both are small compared to the big planets. Both are powerful in what they tell us. One changed a word in our textbooks. The other changed the scale in our minds. Stand back from the lists and the votes, and a simple view remains. Eris made us check our definitions. Sedna makes us check our sense of time. One shows that categories are tools. The other shows that patience is part of the landscape. Neither needs our attention to continue. Eris keeps its 557-year circuit. Sedna keeps its 11,400-year path. They do not hurry. They do not argue. They simply are. That steadiness can feel calm. Eris may have sparked a storm among people, but it is unchanged by the noise. It follows its cold route, bright and steady. The fuss on Earth has already begun to fade. Sedna takes the longer view by default. It moves on, while ages pass elsewhere. If we never send a probe, it will still exist, still turn, still carry its dark red coat under a thin wash of sunlight. It does not need a visitor to be real. From far away, these worlds press one lesson. The map is larger than habit suggests, and the parts we rarely see still matter. Our work is to notice, measure, and understand. Their work is to endure. Eris does so in the scattered disk, with a moon that lets us weigh it and ice that shines like frost. Sedna does so on a path so wide it touches the edge of our model of the sun's reach. Both are quiet, and both reshape what we know. Watch long enough, and the meaning is clear. While we count birthdays and centuries, they count different units. Eris counts centuries by single turns. Sedna counts millennia by single years. The difference is not poetic, it is physical. Distance slows energy. Weak sunlight slows change. Orbits lengthen. Clocks stretch. Landscapes keep their marks. The record holds. If you trace Sedna's arc across a star field, year after year, you would see only the smallest shift. Yet, with patient measurements and careful math, the path emerges. It is a path that pushes us to think in longer spans and bigger rooms. It is a path that says our system does not end at Neptune or at Pluto, or even at Eris. It extends into a space where the sun is almost only an idea, and where bodies still belong to it by a thin thread of gravity. Sedna carries that thread far out. It turns under a pale star, on a course that takes longer than written history, longer than cities, longer than most coastlines. It is not waiting for us. It is not asking to be named. It simply continues a solitary red bead, sliding along a track of frozen space. While we count years, Sedna counts millennia, and to her they are nothing more than the passing of a moment. Begin with balance, not distance. Picture two small worlds sharing a rule set so exact that neither ever strays into the other's path. One is famous, Pluto. The other is quieter, Orcus. The nickname Anti-Pluto is not a judgment. It points to geometry. Pluto and Orcus move on similar tilted paths beyond Neptune. Yet when one is near the Sun, the other is far. And when one is far, the other drifts in. They are partners who never meet. The reason is resonance. Both Pluto and Orcus are in a 3-to-2 orbital resonance with Neptune. For every 3 orbits, Neptune completes. Each of them completes 2. This timing is not an accident. Gravity locks it in. The pattern keeps them from close encounters with Neptune and keeps their long, looping paths in step. Because their positions tend to sit on opposite sides of the Sun, Orcus looks like Pluto's mirror. The symmetry is quiet and persistent, like a metronome buried in the outer dark. Orcus was first noticed in 2004 by Michael Brown, Chad Trujillo, and David Rabinowitz. It began as a faint moving point among fixed stars. With more images and careful math, its path and size came into view. Orcus is about 910 kilometers across, roughly half Pluto's diameter. It is a mixture of ice and rock. Whether it is fully round under its own gravity is still studied. If it is, it fits the dwarf planet class. Its surface is dark, reflecting only a small fraction of sunlight, which points to processes that darken ice over time. Radiation from space changes simple ices. Over millions of years, it breaks and rebuilds molecules, leaving behind a dark, carbon-rich film called tholin. Tholins are not alive. They are complex organics in the chemical sense. On Orcus, they stain water ice grains and lower the surface brightness, giving the world a deep gray-brown tone. Spectra also hint at frozen methane and other carbon compounds mixed with water ice materials that date back to the solar system's early stock. Orcus is not alone. In 2005, astronomers found a moon orbiting it. The moon is called Vanth, a name from Etruscan tradition. Vanth is large compared to Orcus, nearly half its diameter, so the pair sometimes is treated as a binary system. 2 bodies orbit a shared center of mass, each tugging on the other in a slow, steady rhythm. Vanth's surface appears redder than Orcus's, suggesting a different mix of ices and organics. That difference raises 2 origin ideas. The first is a giant impact that threw off a piece of Orcus long ago, which later became Vanth. The second is capture. Orcus grabbed a passing body and brought it into orbit. The exact answer is still under study. From a nearby vantage point, Vanth would circle Orcus in roughly 10 days, a dull red bead around a dark gray stone. The sun would sit low and small. The stars would not twinkle because there is almost no air to shift the light. The pair would look calm, but small changes in the moon's path are valuable. By tracking them, scientists can weigh Orcus, estimate its density, and test models of its interior. Seasons on Orcus are slow and unusual. The orbit is tilted, and the spin axis may be tilted as well. Poles could sit under weak sunlight for centuries, then switch to centuries of darkness. In such a cycle, ices can migrate. Volatile ices, those that turn from solid to gas at low temperatures, like nitrogen or methane, can sublimate in the lit pole and refreeze in the dark one. Over millennia, this process moves frost from place to place and changes the look of the surface in large, quiet ways. The environment is cold and steady. Orcus orbits at a distance where sunlight barely warms the ground above 200 degrees Celsius. Under a thin crust of frozen volatiles, the interior is likely more rocky. Some models allow a layer of slushy water deep below, insulated by ice and kept from freezing solid by leftover heat from radioactive elements in the rock, or by weak tides raised by Vanth. If present, it would not be a wide ocean like Europa's. It would be a patchy, shallow layer that flows very slowly. Still, even a little internal warmth can reset surface chemistry when it reaches the top, whether through cracks, frost cycles, or impacts. Despite its dark face, Orcus is bright enough for precise tracking in medium-sized telescopes, which is how its resonance pattern is mapped with care. The 3-to-2 timing protects it. The rhythm has likely lasted since the early solar system, when Neptune migrated outward and locked many small bodies into this pattern. Pluto drew cameras and headlines with its heart-shaped planes. Orcus drew fewer eyes, but the shared geometry links them, and the link is part of how the outer region stays stable. The name fits the tone. In Roman and Etruscan myth, Orcus is a quiet god of the underworld, less showy than Pluto, but steady and certain. The world that bears the name moves the same way, not in flashes, not with storms, but with timing. If you could stand on its surface, gravity would feel weak a few percent of Earth's. Your steps would be light and long. The ground would be dark and firm, with ancient frost. Vanth would loom large, a fixed presence in the sky if the two are tidally locked, or a slow traveler if they are not. The sun would be a bright star. The rest would be silence and the slow drift of shadows across ice-stained rock. From symmetry to song, another body near Pluto's path carries a name that asks for care in saying it. Quaoar is usually pronounced K-W-A-H-O-R. The name comes from the Tongva people of what is now Southern California, where modern surveys first traced the object's light. In their tradition, Quaoar is a creative force. The fit is practical, not poetic. The name marks a distinct culture and reminds us that the night sky over every place is a shared resource. Quaoar was found in 2002 by Chad Trujillo and Michael Brown. It was one of the first large Kuiper Belt objects after Pluto and paved the way for more. With a diameter of about 1,100 kilometers, Quaoar is larger than Ceres and has enough mass to relax into a nearly round shape. That makes it a strong dwarf planet candidate. The surface is dark, reflecting on the order of 10% of the sunlight it gets, which at this distance is not much to begin with. Spectral data point to water ice and frozen methane, covered by a darker film of tholins. As in other outer worlds, radiation from the sun and cosmic rays break apart simple molecules and build complex ones over long periods, turning bright frost into a reddish-brown coat. Water ice still shows through in places, which hints that the surface is not uniform in age. Fresh ice can be exposed by small impacts that dig through the dark layer, or by slow resurfacing where ice creeps and refreezes. A few studies have suggested gentle cryovolcanic activity, cold volcanoes, that release slushy mixes instead of lava. But that idea remains tentative without a close-up mission. Inside, Quaoar is likely a rock-ice mix. Radioactive elements in the rocky part can supply a trickle of heat for a very long time. If enough heat is trapped by the overlying ice, a thin, briny layer could exist deep below, Briny means salt-rich. Salts lower the freezing point. This would not mean open water or a global sea. It would mean patches where ice behaves like cold honey rather than brittle glass. Even so, pockets of liquid would be important because they can move chemicals around, erase old surfaces when they reach the top, and hold heat longer than dry ice can. In 2023, Quaoar revealed an unexpected feature, a ring. The ring is thin and faint, circling about 4,000 kilometers above the surface. That distance is odd because it is beyond the classical Roche limit, the zone where a planet's gravity tends to pull apart clumps and prevent them from forming a moon. Most rings that we know sit inside that limit. Farther out, particles usually gather into a small satellite over time. Yet Quaoar's ring seems to persist. How? Several ideas are on the table. The particles might be on orbits that resonate with a slow spin, or with a small, unseen moonlet, which keeps them from clumping. The fragments might be too fragile or too fast-moving to merge, or collisions among ring particles might grind any growing clump back down before it can become a moon. The fact that the ring was detected at all by watching the light of distant stars blink as the ring passed in front shows that even small worlds can carry subtle structures. Quaoar's orbit is calm and long. It takes roughly 286 Earth years to circle the Sunday. It lives just beyond Pluto's path, part of the same broad belt of icy remnants left from formation. Seasons last for decades. Day-to-day weather does not exist. There is no thick air to move heat around. Change is slow, over centuries. Patches of frost may build or fade as sunlight shifts and as grains settle. On the surface, gravity would be weak only a small fraction of Earth's. Each step would be a slow arc, and a hop would carry you farther than you expect. The ground would be dark with scattered, lighter grains. Water ice would give a faint sparkle where the sun catches it at low angles. Without air, the stars would look hard and steady. If you looked near the horizon, you might glimpse the ring, a thin, pale band that circles the sky like a drawn line. It would not glow like Saturn's. It would be a precise, quiet feature, visible only in the right light. Quaoar does not show storms like Jupiter or giant bright rings like Saturn. It is not stretched by fast spin like Haumea. It presents a steady face and carries a surprise, a ring where a moon should have formed. That single fact is useful. It tells us that the rules we apply are general guides. Local details can bend the outcomes. It tells us that grains, ice strength, and gentle resonances matter in places where gravity is weak and sunlight is scarce. Naming matters here too. Using Quaoar ties the object to the Tongva language. It adds human context without changing the physics. The name itself does not teach us chemistry or dynamics, but it reminds us that discovery happens in the real world, on land, with its own histories and voices. The sky above Los Angeles County is the same sky where the surveys ran, and the same sky where school students will learn to say K, W, A, H, O, A, R, and point to a map beyond Neptune. Numbers anchor the picture. Orcus spans about 910 kilometers. Quaoar about 1,100. Orcus's albedo, its reflectivity, is modest. Quaoar's is lower. Both sit in the Kuiper belt, a region of small, icy bodies beyond Neptune. Both show water ice and signs of radiation-processed organics. Both likely have rock ice interiors with the potential for slow, small-scale internal heat. Both change on timescales so long that a human lifetime is a short sample. Stand at mental arm's length and let the differences show. Orcus moves in a resonance that mirrors Pluto's path. It carries Vanth, a moon so large relative to its parent that the two almost make a double. Its story is about timing and pairs. Quaoar carries a ring outside the usual line and makes us rethink how rings survive and how moons grow. Its story is about edges and exceptions. Neither world is loud. Both are precise. If you could move between them, the views would rhyme. On Orcus, Vanth would dominate the sky. On Quaoar, a faint ring would draw a circle around you. On both, the sun would be a small, bright disk. Your steps would be light, your shadows sharp, the stars steady. The sense would be of patient motion, long seasons, long orbits, slow change, written in thin layers of frost and dark coatings of tholin. Worlds like these are the leftovers that did not grow into full-sized planets. That word can sound dismissive. Here it is a strength. Leftovers preserve the recipe. Orcus and Quaoar keep a record of early ices, early organics, and early dynamics. They carry that record in dark surfaces, in resonant paths, in a moon's tug, and in a ring that should not last but does. You do not need drama to learn. You need time, light, and careful watching. Return, finally, to the idea of balance. Orcus holds a place that answers Pluto without touching it, a mirror that never meets the thing it mirrors. Quaoar holds a ring that stays where theory says it should fade. Both move on steady clocks that mark centuries instead of months. In the quiet outer belt, where the sun is small and distance stretches every schedule, that kind of order is its own kind of beauty. Quaoar keeps it with a thin halo and a slow spin. Orcus keeps it with a partner and a measured step. Each turns, each endures, and each carries a clean, simple note in the wide, low music of the outer dark. Begin with tilt rather than distance. In the dim Kuiper belt, where the sun is a sharp pin of light, a small crimson world takes a path that leans away from the usual plane. This body is Gong Gong. Most planets circle the sun like beads on a flat plate. But Gong Gong's track is slanted and elongated, cutting diagonally through that plate as if it chose its own lane. It is among the reddest large objects in the outer system, a faint ember against black space, and its steady, off-angle motion makes it one of the most quietly compelling of the forgotten worlds. Gong Gong was picked out in 2007 by a team including Meg Schwamb, Michael Brown, and David Rabinowitz, who compared digital images from Palomar Observatory and noticed a slow-moving speck that refused to stay fixed against the starfield. Its sluggish shift gave away its distance, more than 85 astronomical units from the Sun at the time of discovery. 1 astronomical unit, AU, is the average Earth-Sun distance. As more data came in, the orbit took shape and the size estimate settled. Gong Gong is about 1,230 kilometers across, similar to some of Pluto's distant cousins, and meets the standard for a dwarf planet. The orbit is unusual. At closest approach, Gong Gong comes in to roughly 34 AU. At its farthest, it reaches past 100 AU. The whole track is tilted by more than 25 degrees relative to the main solar plane, and one full circuit needs over 550 Earth years. That slant and stretch suggest a rough past. Early in solar system history, collisions were common. A glancing impact could have knocked Gong Gong into this crooked lane and left marks that still matter. One sign is its color. Gong Gong is deep red. Radiation from cosmic rays and ultraviolet light breaks apart simple ices on outer worlds and rebuilds them into complex organics called tholins. Tholins are not alive. They are carbon-rich residues that darken with time. On Gong Gong, the process seems to have gone further than usual, building thick layers of reddish-brown material, like lacquer laid down over millions of years. Under that coat, the surface is likely a mix of water ice and methane ice. The red tone fits a story where methane frost once covered much of the ground and slowly turned darker under radiation. That change may still be in progress now, grain by grain, as weak sunlight and space particles keep working. Picture a world slowly painting itself red over eons. In 2016, a companion was found, a small moon now called Xiangliu, named for a many-headed serpent from Chinese myth. Xiangliu is roughly 200 kilometers wide and circles about 15,000 kilometers out. By tracing the moon's orbit, astronomers can weigh Gong Gong and show it is denser than pure ice. Rock makes up a significant share of its interior. Xiangliu may owe its birth to the same ancient impact that tilted the orbit material blasted off the surface and later gathered into a stable loop. However it formed, the pair share the far dark, a red primary and a small copper bead moving in step. Gong Gong rotates slowly compared to many Kuiper Belt objects about once every 22 hours, so its days are long and unhurried. Seasons are stranger still. With a tilted orbit, and likely a tilted axis, a pole can face the sun for centuries, while the opposite pole spends centuries in black. In that slow exchange, volatile ices can sublimate in the pale light and drift to colder zones, refreezing as the geometry changes. Somewhere on Gong Gong, a sunrise could span much longer than written history, while on the other side of the world, the shadows hardly move. Temperatures sit near 230 degrees Celsius. Any thin atmosphere that might appear near closer parts of the orbit would freeze and fall back as frost. With almost no air, stars do not twinkle, they hold sharp points. The setting is stark. No wind, no surf, no sound, only the slow fall of light and a surface that keeps its marks for ages. Yet the scene is not chaotic. The orbit is stable. The motion is smooth. The crimson globe and its small moon keep time together, rolling in a lane that ignores the crowd. Stand there in your mind. The sun is a hard white star. Xiangliu rises and sets as a dull copper dot. Each step is a calm bounce in weak gravity, and each landing leaves a crisp print in ancient, red-stained frost. Many dwarf planets keep to the solar plane. Gong Gong does not. It tilts and wanders as if it moves through a second, hidden layer of the system. The name fits. Gong Gong comes from Chinese tradition, a water god with red hair, a figure said to have tilted the heavens, a crimson world with a tilted path, named for a myth about a skewed sky. The link is tidy, but the point is simple. Gong Gong does not rage. It does not conform. It drifts on its own line. Like other small, distant bodies, Gong Gong is probably a leftover from formation, a piece that never reached full planet size. It kept its shape through billions of years, while the inner worlds melted, erupted, and reworked their faces. Here, change is slow. The red coat grew, while planets traded heat and atmosphere closer in. There is a plain beauty in that patience. Gong Gong glows faintly and keeps going, pulling a small moon along its slope, reminding us that the solar system is not only circles and order, it is tilts and outliers and wanderers that still belong. Step back and widen the view beyond Pluto's track. The system does not stop. It thins. Beyond the planets, and beyond better-known dwarf worlds like Pluto and Eris, a population of small, shadowed spheres drifts in the cold. They are not common names. Most show up as faint points, even in large telescopes. Yet taken together they form a quiet family, a spread-out archipelago in the outer deep. One member is Salacia, circling near 43 AU. Named for a Roman sea figure, it is about 850 kilometers across and carries a small moon called Actea. Salacia is very dark, reflecting only a few % of the sunlight that strikes it, so it is dim even among distant neighbors. That low reflectivity points to an old surface, water, ice, and other ices stained by radiation, with a thin layer of organics left after simpler molecules broke apart. Some studies suggest Salacia may be round under its own gravity, which would put it in the dwarf planet set, once confirmed. For now, it is a quiet candidate, following its path beyond Pluto with almost no public notice. Another is Varuna, named after an ancient ocean and sky deity. Varuna is smaller, about 650 kilometers across, but it spins fast, turning once in roughly 6 hours. Rapid rotation has stretched it into an oblong, like a water balloon seen in slow motion. Spectra show water ice mixed with darker carbon-rich compounds. The spin hints at a history of impacts and reshaping, and some models allow for cold, slushy patches deep below where heat from radioactive decay still lingers. Varuna behaves like a small, frozen top at the edge of sunlight's reach, held together by gravity and pace. Ixion adds to the list. The name comes from a myth of a man bound to a wheel, and the object rolls onward at about 42 AU. It is roughly 700 kilometers wide and wears the now familiar dark red-brown of tholins on ice. Ixion follows a path much like Pluto's and likely belongs to the Plutino group bodies in a 3-to-2 resonance with Neptune, completing 2 orbits for every 3 of the giant planet. If Pluto is the famous member of that timing, Ixion is the relative who keeps time just as well without the headlines. Others fill the belt with quiet variety. Vada, about 700 kilometers across, travels with a moon named Il Mare. Both names refer to creative figures from myth. Huya is another reddish body on an eccentric track. Chaos, ironically named, keeps a steady path just beyond Pluto. There is even an object that once picked up the nickname Snow White, later found to be pale red rather than white at all. The color corrected by better data, like so many first impressions in the far dark. Each is small, cold, and still. Together they form a large, unnoticed population at the edge of the sun's reach. The most mysterious part is how many we cannot see. Telescopes catch only the brighter, nearer objects, and only when they are placed just right. Beyond that limit, targets fade below detection. Estimates suggest hundreds, maybe thousands, of dwarf planet-scale bodies may hide in the Kuiper Belt and the region beyond. Some could rival Pluto in size. Many would be smaller than Ceres. Most remain uncounted, their light lost in background noise. That hidden count changes how we picture home. The neat diagram of 8 planets is only the bright core of a broader system. Past Neptune lies a kind of attic, cold, dark, and packed with relics of formation. These icy bodies never gathered enough mass to become full planets, but they did not vanish. They stayed where dynamics threw them, like embers that never cooled below the point of endurance. There is also a live question that hangs over the far region. The orbits of some distant objects seem oddly aligned, as though tugged by something large. One idea is a still unseen Planet 9, a world several times Earth's mass, circling hundreds of AU away. If it exists, its gravity could be gently herding smaller bodies into related paths, acting like a conductor you never see but whose beat you can infer from the players. No one has imaged such a planet. The case remains open, part signal and part selection bias, a rumor that lingers because it would tie several puzzles together at once. Whether that giant is real or not, one truth holds: beyond Neptune, the map fades. The distances are large, the light is weak, and the skies crowded with stars that hide faint movers. We have charted what is bright enough near Pericenter, the closest point in an orbit to appear in surveys. Beyond that, the page goes blank again. Salacia, Varuna, Ixion, and their kin are the visible tips of a much larger ice-gray mass of worlds. That fact is humbling. We live in a system that feels familiar, but most of its members are invisible most of the time. The big planets are grand halls near the center. Around them spreads a quiet suburb of frozen wanderers, each holding a piece of an early story in its surface chemistry and its path. They are the pages left in the binder after the first draft was done, still where they were filed. Imagine that spread all at once. A sphere of orbits thousands of times wider than Earth's path around the Sun, dotted with small bodies that turn slowly and rarely change. Each one is alone and yet part of a hidden set that we are only beginning to notice. It is steadying to remember that while our days move quickly, those worlds move with patience. They do not flash or call for attention. They circle century after century, waiting until a survey happens to catch their light. So, the solar system is not only clockwork, it is also a sprawling archive, half forgotten in places. We know the bright titles on the front shelf. Most of the collection sits deeper in the stacks, dusty and dim. The small, distant dwarfs read like footnotes, but together they can shift the story's weight. Past the familiar planets, past the named dwarf worlds, there may be an entire hidden branch still out there, a silent archipelago of icy spheres turning slowly in the dark, patiently keeping their place on the edge of the sun's light. Begin with structure rather than distance. Past Neptune's path, the solar system does not stop. It thins into a wide band of small, icy worlds, moving on slow, steady tracks. This region is the Kuiper Belt, a ring of leftover material from planet building. It starts just beyond Neptune, near 30 astronomical units from the Sun, 1 AU is the Earth-Sun distance, and stretches outward for at least another 50. If the inner system feels like a bright, crowded city of planets, the Kuiper Belt is open country, quiet, cold, and lined with objects that have changed very little in billions of years. The name honors astronomer Gerard Kuiper, who argued in the mid-20,000th century that a reservoir of icy bodies likely existed beyond Neptune. Others had suggested similar ideas before him, but when the first objects beyond Pluto were found in the 1,990 seconds, the name Kuiper Belt stuck. Since then, thousands of bodies have been catalogued, and there may be billions in total icy remnants from the solar system's youth still circling where they were placed. To see how they formed, rewind to about 4.5 billion years ago. A wide disk of gas and dust surrounded the newborn Sunday. Within that disk, tiny grains of rock and ice collided and stuck together. Over time, clumps grew into boulders, then into kilometer-scale bodies. These are planetesimals, early building blocks with enough gravity to pull themselves into tighter shapes. Close to the Sun, heat drove off most ices, so only rock and metal remained to build Mercury, Venus, Earth, and Mars. Farther out, where temperatures were low, ice was plentiful. The giant planets formed there and vacuumed up most of the local material, but not all. Many icy planetesimals were tossed outward by the gravity of Jupiter, Saturn, Uranus, and Neptune. The Kuiper Belt is where a share of those survivors ended up, a population of leftovers that never grew into full planets. Most Kuiper Belt objects, KBOs, are small tens to hundreds of kilometers across and irregular in shape. They are made mainly of frozen water, methane, nitrogen, and carbon-bearing compounds mixed with rock. Many look dark because of tholins, complex organic residues that form when ultraviolet light and cosmic rays slowly alter simple ices. A few bodies, Pluto, Eris, Haumea, Makemake, are large enough to be nearly spherical and are classed as dwarf planets, but they are the big end of a population mostly made of fragments. Despite the phrase belt, the region is sparse. If you stood on a small KBO, the nearest neighbor might be millions of kilometers away and no brighter than a sharp star. Distances are so large that, although the belt holds a huge number of objects, space itself dominates. There is no crowded rock swarm like in movie scenes. Orbits take centuries to millennia. Collisions do happen, but they are rare and slow by cosmic standards, more like two drifting icebergs bumping than a fireball. Over eons, these gentle encounters can grind surfaces smooth, refresh frost, and toss fine particles into space, slowly reshaping the belt, grain by grain. Sunlight out here is weak, hundreds of times dimmer than at Earth. It acts more like a lamp than a heater. Surfaces stay near 200 degrees Celsius. Any gas that boils off the ground tends to refreeze quickly. With no air to blur edges, craters and ridges remain sharp for ages. In that way, the Kuiper Belt preserves history. Its objects are time capsules from the early solar system, storing the starting materials, water ice, methane, nitrogen, carbon compounds that later helped shape atmospheres and oceans on the inner worlds. It is striking to consider that small, silent KBOs likely delivered part of Earth's water and organics through impacts, setting conditions for life long after the main building phase had ended. Pluto was the first known member of this distant family, discovered in 1930. For decades, it seemed alone, the single outpost at the system's edge. Then, in the 1,990 seconds, surveys began to find more. Quaoar, Varuna, Ixion, Haumea, Makemake, Eris, and many others appeared one by one. The picture changed. Pluto was not an oddball. It was part of a broad, ancient region, rich in small worlds. That shift reshaped how we draw the solar system. The Kuiper Belt is not a thin border. It is a wide hinterland that has been there since the beginning. Within this region, orbits sort into families. Classical KBOs follow nearly circular, stable paths that have likely changed little since formation. Resonant objects are locked in step with Neptune. A resonance is a timing pattern maintained by gravity. Pluto, for instance, is in a 3-to-2 resonance with Neptune. While Neptune completes 3 orbits, Pluto completes 2. The geometry keeps them from close approaches even though their paths cross in space. Other bodies share similar locksteps at different ratios. A third group, the scattered disk objects, occupies elongated, tilted orbits that likely started when Neptune migrated outward and flung small bodies into stretched paths. These scattered orbits blur the outer edge of the belt and lead toward an even more distant population. Taken together, these icy worlds form a kind of cosmic gravel road material left over after the major planets cleared most of their neighborhoods. Leftover does not mean failed, it means preserved. The belt is less a graveyard than a museum. If you could look from above, you would see a broad, thin ring speckled with tiny points, each on its own slow schedule. And beyond this ring, the darkness deepens. Past the Kuiper belt, neatness fades. The solar system's outer zone grows rougher. Here is the scattered disk, a region where the sun's pull is still present but no longer tight, and where orbits tilt and stretch into wide, wild ellipses. Objects there swoop above and below the ecliptic, the main plane of the planets at sharp angles. Some inclinations reach 40 degrees or more. Paths lengthen so much that a single loop can span hundreds of astronomical units. The space between neighbors grows to billions of kilometers. Each object moves mostly alone. Eris is the best-known example. It is a dwarf planet that spends much of its 557-year orbit beyond the main Kuiper belt, swinging out toward 100 AU and coming back to around the high 30 seconds. At its farthest, the sun would look like an intense star, and sunlight would take nearly 9 hours to arrive. Eris is not unique. Other scattered objects carry their own extremes. 2004 XR 190, nicknamed Buffy, rides an unusually high inclination track. 2007 TG 422 follows a loop that takes roughly 1,400 years to complete. Each path is its own lesson in dynamics, long, solitary, and tilted well out of the main plane. How did these bodies get scattered? The story traces back to the system's unsettled youth. As the giant planets formed, they did not stay exactly where they began. Jupiter and Saturn shifted their positions. Neptune likely migrated outward. As it moved through a disk of small icy bodies, Neptune's gravity worked like a slow snowplow, capturing some objects into resonance and flinging others outward onto elongated orbits. Many were tossed clear of the system and lost to interstellar space. Some remained bound to the sun on stretched and tilted tracks. These became the scattered disk. Other influences may have joined in. Early on, the sun probably lived in a dense star cluster, a passing star far distant by everyday standards, but close in astronomical terms, could have tugged at the outskirts of the young system and pulled small bodies onto wider, steeper paths. There is also the periodic idea of a long-lost planet, an ice giant formed closer in, then ejected during gravitational shuffling, disturbing orbits as it went. Any of these processes, or a mix, could seed the population we see now. The environment is sparse and still. With sunlight so weak, surfaces remain deeply frozen. Without air, nothing smooths or erases features. Craters keep their edges. Fine dust sits where it lands. If you could stand on one of these objects, the sun would pierce the sky as a white point, and the stars would look razor sharp. The nearest other world would be too far to see. Gravity would be faint. Each step would feel slow and buoyant, and the horizon would be low and dark. The scene would be quiet enough that the passage of time would feel stretched. Time is the key difference. While Pluto takes about 248 years to orbit, many scattered bodies need thousands. At aphelion, their farthest point, they barely move across the star field. Seasons, if they exist, can last for centuries. Some of these objects likely serve as a bridge to something even more remote, the Oort cloud, a vast, spherical shell of icy bodies that is thought to surround the solar system. Many long-period comets that sweep into the inner solar system may begin as bodies from the scattered disk. Over ages, small nudges push them outward until they settle in the distant comet cloud. And much later, a passing star or the slow pull of the Milky Way tips them back inward again. In that sense, the scattered disk is a middle ground between the well-mapped solar system and open interstellar space, a twilight region where the sun's grip loosens and the galaxy's tide starts to matter. These objects are hard to find. They are small, dark, and slow. Across months or even years, their change against the background stars is barely there. Most are likely still unseen. What we detect are the brighter and nearer few, the ones that happen to wander close enough for our surveys to notice. Each new dot widens the charted edge, pushing our known boundary outward one careful step at a time. For all their distance and disorder, scattered disk objects are not random pieces. They are survivors of an old upheaval. Their tilted, stretched paths record the solar system's early turbulence, the reshuffling that happened when the giant planets moved and traded angular momentum. The neat pattern of today's planets is the calm that followed. These frozen bodies are the notes that stayed in the margins. Look at them one by one, and each path feels unique. Step back, and you see a diffuse halo moving in slow counterpoint to the regular planets. They are distant echoes of formation, still circling the sun at the edge of its reach. While the inner worlds spin and weather and trade heat, the scattered disk moves in quiet arcs. It is easy to forget they belong to the same family as Earth. They are far, and they act with restraint. Yet the same sunlight that warms oceans and drives winds also reaches them, thin but steady. The scattered disk shows how far that reach goes, how faint and stubborn the sun's pull can be. Order phrase, orbits tilt and lengthen, but the link remains. The bodies roam, and they remain bound. Far beyond this restless rim lies a place so remote and so calm that no camera has seen it directly. This is the Oort cloud, if it exists, as most models indicate. Think of a vast, spherical shell of icy objects that surrounds the sun and all the known planets. It is not a ring, not a belt, but a bubble. At that distance, the sun would look like a bright star among other bright stars. The Oort cloud is still an inference. No spacecraft has flown through it and identified members. No telescope has imaged single objects there. Its presence is drawn from patterns in long-period comets, those rare visitors that appear from the deep dark, with orbits so wide and stretched they cannot come from the Kuiper belt or the scattered disk alone. Some take millions of years to go around once. The simplest source is a reservoir far outside the planets, a cloud of small, icy bodies stirred now and then by passing stars or by the slow gravity of our galaxy. If the cloud is real, it is enormous. It may begin around 2,000 astronomical units, AU, from the Sun, and extend to tens of thousands of AU, perhaps near 100,000. Earth orbits at 1 AU. Pluto's average distance is about 30 AU. The outer cloud could be more than 3,000 times farther than Pluto. Near that edge, the sun's pull is so weak that it only barely holds on. Beyond it, the gravity of the Milky Way and of other stars competes and can take over. The cloud would be the fading edge of the sun's domain, the place where home starts to blur into the larger neighborhood. What would live there? Likely trillions of small icy bodies, a few kilometers wide, and countless more the size of hills or mountains. They would be made of water ice, methane and ammonia ices, and dust mixed with rock leftover material from the solar system's early days. When the giant planets formed, their growing gravity flung huge numbers of icy planetesimals outward. Most escaped the system. Some slowed just enough to stay bound. Over time, the tug of passing stars and the gentle galactic tide nudged those survivors into a diffuse, nearly spherical cloud. Once placed there, little changed. There is not much heat, not much light, and almost no chance of collisions. Objects simply coast. If you could perch on one more, like standing on a drifting iceberg, than a planet, the sun would be a sharp point, bright but small. The nearest neighbor might be millions or billions of kilometers away. The sky would be black, full of steady stars. Underfoot, ancient ice marked by craters that have never softened, dust that has never been moved by wind. Time would feel different. In the outer cloud, one orbit could take tens of millions of years. Even the inner cloud would hold paths measured in millions. Against that scale, the familiar planets whirl like bees. The cloud moves at the pace of continents rising and seas opening slow, patient, and long-lived. Sometimes, the quiet is disturbed. A star passes near our system and tugs at a few fragile orbits. The galaxy's broad pull does the same on longer timescales. Such small nudges can send an object drifting inward, falling for ages until it enters the inner solar system as a long-period comet. Near the sun, heat turns buried ices into gas, and sunlight pushes dust into a tail. A faint iceberg becomes a bright visitor for weeks or months, then fades and heads back out. These comets are our messengers from the cloud. Their dust carries water, carbon compounds, and organic molecules, simple building blocks that also appear in meteorites and that likely played a role in early chemistry on Earth. Each bright arc across the night is a sample from that hidden halo. The Oort cloud may be the largest structure tied to the sun and also the hardest to confirm. Its pieces are too small and far to reflect much light. Their motion is too slow to track directly. We infer the cloud the way sailors infer a current, by watching where driftwood comes from. Long looping comet paths point back to a broad, unseen source. The image that forms is striking. The planets, the Kuiper belt, and the scattered disk are the bright inner rooms. The Oort cloud is a dark, hollow hall surrounding all of it. It would not bustle or shine. It would simply be vast, cold, and slow set between the pull of our star and the pull of the galaxy. It might also be shared at the edges. The sun likely formed in a cluster with many other stars. Over billions of years, close passes could have traded cloud members. Some models suggest the outermost zones of our cloud overlap with similar clouds from other stars, a mingled border where small worlds drift without a clear badge of origin. In that view, the Oort cloud is not just our limit. It is the start of the in-between, where one system's leftovers blend with another's. Direct exploration is far beyond what we have done. Voyager 1, our most distant probe, is a bit beyond 160 AU. If the inner edge of the cloud begins near 2000 AU, Voyager is not close. Crossing the cloud would take it tens of thousands of years, and even then, the craft would sweep through silently, passing far from any object large enough to notice. The spacing is too wide for a flyby by chance. Even so, the cloud matters. It shows that the solar system is layered, Not just a tidy stack of 8 planets on a flat sheet. There is a warm, bright center and a faint, cold halo. The sun's grasp reaches farther than intuition, holding on to small, forgotten pieces with a delicate touch. The Oort cloud is the soft edge of that grasp, the place where our star's gravity eases into the galaxy's tide. It is dark and distant and quiet, but it sits on the same ledger as everything inside. It is the oldest record of how our system began, and it is where the last small fragments will keep their paths, circling a sun they can barely see. Before the solar system became a tidy set of planets, it was a wide, rotating disk of gas, ice, and dust around a young Sunday. There were no worlds or moons, only tiny grains drifting in warm light. Yet those grains held all future landscapes in small, simple form. Mountains, oceans, and air were not built yet, but the ingredients were present and moving. In that quiet chaos, the first steps toward worlds began. Growth started at the smallest scale. Dust motes bumped and stuck by electrostatic forces, forming fluffy clumps. Most impacts broke those clumps apart again, but time was generous. Over millions of years, some pieces survived long enough to grow. As they collected more grains, they became pebbles, then rocks, then boulders, and eventually, kilometer-sized bodies called planetesimals, early building blocks with enough gravity to pull in more material. The young solar system was crowded with these bodies. They circled the sun on paths that crossed and overlapped, merging when speeds were gentle and shattering when speeds were high. It was both a construction site and a demolition yard, and every later planet was shaped by that steady grind. Where material was dense, closer to the sun, growth ran faster. As some planetesimals reached hundreds or thousands of kilometers across, gravity rounded them into spheres and their interiors warmed. Heat came from radioactive decay and from the energy of repeated impacts. Heavy elements like iron sank toward the center, while lighter silicates and ices rose. This separation, called differentiation, turned rubble piles into layered worlds. The largest cleared their orbits of smaller neighbors and earned full planetary status by dominating their zones. Farther out, the disk was colder and thinner. Material was spread out. Collisions were less frequent, and growth slowed. Many planetesimals never reached the mass needed to sweep their lanes clean. Some were nudged inward by bigger bodies and became captured as moons. Others were slung outward by the gravity of giant planets, settling into the scattered disk or even the far comet cloud. Many simply stayed put in distant orbits. Their growth stalled early. These are the forgotten worlds, dwarf planets and icy remnants that never joined the inner stage. Forgotten does not mean unimportant. They are best thought of as fossils, preserved samples of how planet building looked before the big changes finished the job. While Earth, Venus, and the rest were reshaped by volcanoes, oceans, and plate motion, the dwarfs kept their ancient marks. Their surfaces still carry craters from the heavy bombardment period, and their interiors often remain much as they formed. Near misses were common. Some bodies grew to near planet size only to be shattered by a badly timed collision. Others might have become planets if they had formed slightly closer to the sun, where feedstock was thicker and growth rates were higher. A few were on track to gain mass, but were flung away during the migration of the giants, exiled to orbits where further growth was impossible. The modern system is filled with these what-ifs. Each dwarf planet is a survivor of paths that almost led to something larger. The difference between a planet and a dwarf planet is more than a simple size cut. Pluto is smaller than Earth's moon, yet it is complex and active. The key factor is dynamical dominance. Planets clear their orbits, sweeping up or ejecting smaller bodies so they rule their orbital zones. Dwarf planets did not reach that stage. They remain in company with many neighbors on similar paths, more like actors who showed up for the audition and still stand on the side of the stage with the same lines they had at the start. Shape also tells a clear story. A body becomes round when its gravity overcomes the strength of its rock or ice and pulls it into hydrostatic equilibrium, a nearly spherical form. Cross that threshold and you get a dwarf planet. Miss it and you keep an irregular shape. Ceres reached it in the asteroid belt. In the Kuiper belt, Haumea, Makemake, and Eris reached it too, though Haumea's rapid spin leaves it stretched. Most nearby neighbors never crossed that line and remain lumpy, like shards of a broken vessel left in sunlight. In the cold outer zones, some planetesimals grew fast enough to become cores of future giants before the sun's early wind stripped away the remaining gas. Those cores pulled in hydrogen and helium to become Jupiter and Saturn. Uranus and Neptune formed as ice giants, rich in water, methane, and ammonia ices mixed with rock. When the gas dispersed, the window for making more giants closed. After that, no other planet could follow the same path. No matter how long it waited, timing decided outcomes. The giants rose quickly. The dwarfs lingered and kept to quiet routines. The line between made it and didn't was thin. A small shift in position or a small delay in growth would have changed the cast. Pluto might have become a minor planet. Mars might have stayed stunted longer. Ceres could have merged with neighbors and built a true planet between Mars and Jupiter rather than ending as the belt's largest body. Haumea might never have been reshaped by a violent impact. Sedna might have avoided its huge, thousands-year orbit and remained nearer the planets. What we see is the patchwork that survived: chance wins, near misses, and a final layout influenced by migrations and encounters. The process we reconstruct here is not unique to our Sunday telescopes now image protoplanetary disks around young stars, rings and gaps carved by growing bodies. In those systems, the same story is beginning again. Some worlds will reach the mass and timing needed to dominate their orbits. Many will not. Countless small bodies will remain in outer belts, enduring as cold files of early history. That is not a failure mode. It is the natural outcome of disk physics and time. Planetary systems are not perfect grids. They are families, a mix of large and small, busy and quiet, finished and unfinished. The quiet members matter. They delivered ingredients to the inner worlds. Collisions from icy bodies likely brought part of Earth's water and a share of its carbon and nitrogen. They also preserve the raw chemistry of the early disk: water ice, methane, nitrogen, and complex organics formed by radiation on frozen surfaces. The giants may command attention, but the dwarfs are the scaffolds that let giants form and the couriers that stocked young planets. They are not broken worlds. They are stories that paused early and stayed legible. As our view widened, our language had to catch up. For most of human history, planet meant wandering star, points that moved against fixed constellations. Mercury, Venus, Mars, Jupiter, and Saturn were known by eye. The telescope expanded the list. Uranus in the late 1700s, Neptune in the 1800s, Pluto in 1930. For decades, school charts listed 9 planets with confidence. Then new surveys lifted the horizon. The outer system turned out to be crowded, and the neat list blurred. Where did planets end and minor bodies begin? Between moons, asteroids, comets, and dwarf worlds, categories overlapped. By the early 2000s, one fact was hard to avoid. Planet had never been defined with care. It was a tradition, not a test. That tradition cracked when Eris was found in 2005. Eris is slightly smaller than Pluto in diameter, but more massive. If Pluto was a planet, why not Eris? If Eris counted, what about the many Pluto-scale bodies being found beyond Neptune? Should the list leap to 10, 12, or dozens? A term that had felt solid for generations was at risk of stretching until it lost meaning. In 2006, the International Astronomical Union met in Prague to set a standard. After debate, they voted on 3 criteria for planethood. First, the object must orbit the Sunday. Second, it must be massive enough for its gravity to pull it into a nearly round-shape hydrostatic equilibrium. Third, it must have cleared its orbital zone of other bodies, dominating that region. Pluto met the first 2, but not the third. It shares space with many Kuiper Belt objects and does not control its neighborhood. Pluto was reclassified as a dwarf planet, along with Eris, Ceres, Haumea, and Makemake. The official planet count dropped from 9 to 8. Posters changed. Memory aids were rewritten. Many people felt a personal loss. Pluto had been part of their mental map since childhood. The decision triggered arguments beyond nostalgia. Some scientists pointed out that clearing the orbit was vague and seemed to penalize small outer worlds. Earth, after all, shares space with thousands of near-Earth asteroids. By a casual read, no planet perfectly sweeps its lane. Others answered that without a dominance rule, planet would swell to include hundreds or thousands of objects, and the word would stop being useful. Beneath the dispute sat a deeper question about how we classify. Do we define a planet by what it is, its mass and shape, or by what it does in context, its control over a region? The IAU's definition leaned on location and behavior as much as on size and roundness. 2 objects of the same mass and composition could end up with different labels if one lives alone and the other lives in a crowd. Pluto would count as a planet if it orbited alone near Earth's distance, but in the crowded Kuiper Belt, it is classed as a dwarf. That rule keeps the list compact, yet it can feel arbitrary, as if Pluto were penalized for living in the wrong neighborhood. The discussion did not end in 2006. Since then, many astronomers have argued for revisiting the definition. One proposal is simpler. If a body is large enough to be round, held in a nearly spherical shape by its own gravity, it should be called a planet, no matter where it lives. That single change would restore Pluto and promote dozens of round outer worlds, enlarging the family tree. Others prefer new umbrellas, like planetary mass objects or worlds, categories that include both the traditional 8 and the dwarfs, without relitigating names. There is debate over another clause in the definition. Orbits the Sunday. Moons such as Ganymede and Titan are larger than Mercury and show rich geology, thick atmospheres, seas of methane, subsurface oceans, yet they are excluded because they orbit planets, not the Sunday. Some researchers argue for calling them satellite planets. Others want to preserve planet strictly for star-orbiting bodies. Even exoplanets were not part of the original wording, though common usage rightly includes them now. All this reveals a basic truth. Planet is a label we build, not a law of nature. The The universe does not draw hard lines between planets and non-planets. It assembles worlds of many sizes, compositions, and orbits. Our categories are tools that evolve with understanding. Once, the Sun and Moon were counted as planets in the old sense of wandering lights. Once, Ceres and Vesta joined the list before being reclassified as asteroids. Now Pluto has moved to the dwarf planet group. Future discoveries will shift the language again. The outer system keeps blurring edges. Some asteroids show signs of past volcanism and water alteration. Some comets behave like dormant, rocky bodies wrapped in ice. Dwarf planets stand between minor body and major world, with geology active enough to rewrite old assumptions. Moons complicate things further. Europa and Enceladus are small, but they may host global oceans under ice. Io is volcanic beyond anything on Earth. The deeper we look, the less useful hard boxes become. The solar system reads like a spectrum, large to small, round to irregular, quiet to active, airless to atmosphered, each object, the outcome of its own birth and orbit. Pluto's reclassification was never only about Pluto. It was driven by the wave of worlds found beyond Neptune, Eris, Haumea, Makemake, Sedna, and many smaller bodies. Those finds forced a decision. Either the list of planets swells into the dozens, or we reserve the term for the few that dominate their zones. The definition changed to make space for everything else we were finding. In doing so, it also exposed how provisional our names are. Labels crack when reality resists tidy borders. There is a certain clarity in that. Words are scaffolding. They can be rebuilt. The worlds continue unbothered. Pluto still turns in sunlight. Eris shines far beyond. None of them care what we call them. The debate reflects our need to sort the cosmos cleanly in a universe that is cheerfully messy. The concept will change again as we map new systems, drill new moons, and expand our reach. A future generation may smile at the 8-planet model as quaint. They may call hundreds of objects planets, or retire the word and talk instead about worlds, each with its own facts and history, all part of the same family. Whether Pluto carries a certain label matters less than the fact that it exists as a real place, with weather, mountains, and layered ices. The same is true from Mercury to Sedna, from dwarf to giant. Names shift. Geology and orbit remain. The work of classification is not about drawing a final border. It is about learning how wide and strange our system is, and keeping our language flexible enough to follow. Most of the small outer worlds are still only moving points in deep images, faint, slow specks tracked across starfields. Their maps are blank. Their craters and ridges sit behind distance and darkness. That will change. The urge to explore has always pulled outward, and the outer solar system is the last great shore. Future missions will glide past these quiet bodies, letting their surfaces unfold frame by frame in dim sunlight. We have already taken a major step. In 2015, NASA's New Horizons flew by Pluto after nearly a decade in flight, turning it from a dot into a detailed world. Cameras revealed bright nitrogen ice plains shaped like a heart, blocks of water ice standing like mountains, and a thin, hazy atmosphere arching away from the surface. That single pass reframed Pluto from symbol to place active, layered, and complex. The same spacecraft kept going, and on the first day of 2019, met Arakoth, formerly 2014, MU-69, a small contact binary, about a few tens of kilometers long, shaped like two flattened lobes gently joined. Its surface is smooth and lightly cratered, tinted red by tholins formed over billions of years. Arakoth showed us what a very primitive building block looks like. Material that never melted or mixed deeply, preserved since the system's earliest days. It was a direct glimpse into the first chapter. Those results sharpened the appetite for more. Concept studies sketch flybys of Haumea to examine its rapid spin, elongated shape, and narrow ring. Orbiters for Eris to weigh it precisely and map the chemistry of its bright, frosty surface. Tours that hop among several Kuiper Belt objects to compare surfaces and colors under the same instruments. Distances make such journeys long. Eris, for example, can be more than 14 billion kilometers from the Sun at aphelion. Even at New Horizons-like speeds, a mission would need over 2 decades to arrive. That timescale does not erase the goal. Deep space work moves on patient clocks, and the targets have waited for eons. A few more decades fit their pace. Engineers are exploring new ways to go faster or lighter. Solar sails could ride photon pressure outward with no propellant, angling like kites to gain speed. High-efficiency ion engines could sip fuel for years, accelerating gently to record velocities. Some plans stack gravity, assists, dives near planets, or even a close pass by the Sun to sling a probe into the outer dark with added energy. Ideas mature slowly, but so did every mission we now treat as standard. When Pluto was discovered, a probe like New Horizons would have sounded like fantasy. Bit by bit, designs become hardware. Closer to home, Dawn's mission to Ceres showed what an orbiter can do around a small world. From 2015 to 2018, Dawn mapped bright salt deposits in Okata crater sodium carbonates likely left behind by briny water that reached the surface and evaporated. It charted Ahuna Mons, a young cryovolcanic dome, and found signs that brines may still exist deep below. Those results left crisp questions. How thick is any remaining liquid layer? What chemistry runs there? How long can a small world stay active in the cold? Follow-up missions could carry penetrators or small landers to test the subsurface, take samples of salts, and listen for tiny quakes that hint at motion within. Beyond the asteroid belt, planners imagine a portfolio rather than a single flagship. A series of smaller flybys that together build a comparative picture. A Haumea pass would look for fresh crystalline ice, map the ring's structure, and measure shape and density to constrain the interior. An Eris flyby would target its nitrogen and methane ices, map Dysnomia's orbit for mass, and watch for seasonal frost changes. A Sedna flyby would be harder but powerful, imaging one of the most distant known bodies and sampling the deep red tholin coating that likely records billions of years of radiation processing. Timelines would be long. Signals would take hours to cross the void. Spacecraft would need autonomy, choosing when to switch instruments, when to track a target, and how to ride out a sudden glitch without waiting for instructions from Earth. The discoveries would come slowly by design. Each approach would begin as a dot, become a disk, then reveal texture. A scar here, a smooth plane there, a faint haze, a narrow ring drawn thin across the sky. It would feel like watching an island rise from mist. The pace matches the subjects. These worlds change in inches per century. Their surfaces keep craters for ages. Their thin atmospheres, if present at all, come and go, with seasons that last decades. A fast look would miss most of the story. A slow, careful pass suits them. The cameras would simply record what is there, letting the geology and chemistry speak. Perspective is part of the payload. From far out, the sun shows as a bright star. Seeing it that way, over the shoulder of a small world, links scales that are hard to connect from home. One star lighting every sea and field here, and also lighting a faint ring around a dwarf planet beyond Neptune. When New Horizons looked back at Pluto, it saw a blue atmospheric haze against space. Then, beyond that, the sun as a point. That image compresses ideas. A thin sky over an ice world, the same physics at work on a tiny scale as on a giant one. The same light traveling billions of kilometers to sketch a rim of color. Future views from Eris or Sedna would do something similar. Even a quiet, airless surface can teach, just by showing what endured. Eventually, landers may follow. A small robot on Makemake could drill a short core through dark, tholin-rich crust into clean ice and heat a grain to read its gases. A hopper at Orcas could test for fresh water ice exposures and listen with a simple seismometer for the creak of cooling ice. Power would be scarce. Sunlight is weak. These platforms would work slowly, waking and sleeping, sending thin packets of data across billions of kilometers. They would be emissaries more than machines, patient instruments left to keep watch. Such missions would not deliver quick victories. Commands would arrive late, and results would come in steady trickles. But that is the right rhythm. The outer system is not a place for rush. Each success would be a careful piece placed on a larger map. A confirmed ring here, a crust composition there, a measured density that changes an interior model, a moon's orbit that tightens a mass estimate. Over time, the blank edges would retreat. In the end, exploration out here is also about language. As images and spectra accumulate, our labels will follow. Maybe we will widen planet again. Maybe we will lean on worlds as the flexible term that fits what we find. Either way, the places themselves will lead. A flyby of Eris that reveals seasonal frost and subtle haze bands is a result whether we call Eris a planet or a dwarf. A Haumea pass that maps a fresh ice patch near its ring is a result no matter which box it sits in. The outer system invites that kind of humility. It offers worlds that are small yet complete, cold yet active enough to leave clues, distant yet reachable with careful planning. They have been steady for billions of years. They will be steady when our first probes arrive. When close-up images of Eris or Haumea or Sedna finally come home, they will not show emptiness. They will show long-kept records. Old ice, old scars, old chemistry held in quiet places. They will remind us that exploration is not only about speed or range. It is about patience, attention, and a willingness to let the subject set the tempo. The probes will drift with curiosity as their guide. The worlds will accept the visit without hurry. They have waited across ages, and when we arrive, they will still be there, turning gently under the pale sun, ready to be seen. In the family portrait of our solar system, the small, distant worlds barely register. They sit far from the sun's warm light. They do not roar with storms like Jupiter or wear bright rings like Saturn. They do not shine blue like Earth or glow red like Mars. At first glance, they look like footnotes, leftovers, fragments, quiet objects that never became anything more. Yet, they matter deeply. These are the keepers of memory. Inside their frozen crusts, they hold the story of how everything began. While the big planets stirred themselves with volcanoes, oceans, and shifting crust, these outer worlds stayed almost unchanged for billions of years. Their surfaces still carry scars from the era when rock and ice rained down. Each crater is a mark from that long-ago storm. Grains of dust on those plains can be older than any mountain on Earth. They are true time capsules, sealed by cold and darkness since before life arose. Their materials tell the tale. The forgotten worlds are made of the same stuff that once filled the disk around the newborn sun. Water ice, methane and ammonia ices, carbon-rich compounds, and silicate rock. The larger planets used, melted, or buried most of that mix. The dwarfs did not. They stayed small and kept the original chemistry. Sampling them would be like dipping a spoon into the solar system's first soup, still chilled and stored at the edge of space. They likely shaped our own world as well. Many scientists think part of Earth's water arrived from icy planetesimals that fell inward long after our planet formed. Early Earth was too hot to keep much water. Later, waves of small, icy bodies struck, releasing vapor that rained out into oceans. Those same impacts probably brought organic molecules, simple carbon-bearing building blocks. Without those deliveries, Earth might have stayed a dry stone under a blank sky. If so, clouds, rivers, and even the air we breathe carry a quiet debt to those far-off wanderers. There is more. Radiation from the sun and from space can break simple ices on these worlds and let the pieces recombine into complex organics called tholins. Tholins are reddish-brown and coat many dwarf planets like a thin varnish. On Earth, similar organics likely swam in the early seas where life first took hold. To find them frozen billions of kilometers away is to glimpse a mirror of our beginnings. Their orbits teach as well. The way these bodies move shows how the giant planets shifted long ago. Neptune seems to have drifted outward like a slow tide, scattering small objects as it went. Some were flung into the scattered disk. Some were tossed into the distant comet cloud. Some were caught in resonances, timed patterns like Pluto and Orcus, which dance to Neptune's rhythm and avoid close encounters by precise geometry. The pattern of paths is like fossil ripples in space. By tracing them, scientists can rebuild the hidden history that took place before Earth ever cooled. Their silence matters too. The forgotten worlds show that size is not the same as importance. They are not loud. They do not flash with lightning or send geysers into space by the ton, and when a few do, they do it softly. They simply keep their places at the edge of sunlight. In doing so, they reveal the full shape of the system, not only the 8 planets we know well, but a wide architecture of small things. Even their slight gravity nudges the paths of dust and comets and helps set the flow of material far from the sunday. They give us perspective. From Earth, rich with air and life, it is easy to feel near the center of all things. From the distant edge, Earth is a pale point near a brighter one. The small worlds out there feel calm. Not all of existence must move quickly. Some parts endure by barely changing. Their stillness throws our rush into relief. It is a steady backdrop that makes every spark seem bright. Their beauty is modest but strong. Pluto shows soft plains of nitrogen ice. Haumea spins fast, stretched into an icy oval. Makemake glows a gentle red under starlight. Sedna drifts on an orbit that lasts about 11,000 years. Each is a frozen work shaped by time. Distance hides their details, and that makes the beauty more precious. They do not call for attention. You must look with patience to see them at all. That is part of their gift. They train us to notice what we would otherwise pass by. It is easy to marvel at Saturn's rings or Jupiter's storms, It is harder to feel awe for a dim speck that crawls slowly across a star field, but that dim speck can be older than any mountain, richer in memory than any library, and packed with clues about how planets form, how water and organics spread, and how solar systems grow. These worlds ask us to slow down. They ask us to pay attention. They ask us to find the extraordinary inside the quiet. They also remind us that the solar system is not arranged for our convenience. It is not tidy. It is a sprawling family of worlds, some bright, some faint, some large, some small. The giants near the middle and the dwarfs at the edge are made from the same stardust and shaped by the same forces. To value only the large is to miss most of what exists. To value only the bright is to miss most of what endures. Even if no person ever stands on Sedna or watches a sunrise over Orcus, their existence enriches the story we try to tell. They show how generous creation is. It made far more worlds than were needed and let them wander in quiet arcs for billions of years. They are not forgotten by the cosmos. They are simply patient. They keep their orbits whether or not we notice. This, finally, may be their central meaning. Wonder does not require scale or spectacle. It requires noticing. A single seashell can hold the idea of an ocean if you look closely enough. The giants roar, the small ones endure. Think of them as the punctuation marks in the solar system's sentence, the soft pauses that give the rest of the story shape. Without them, the tale would be shorter and flatter. With them, it has depth. They carried water to our seas, carbon to our soils, and history to our understanding. They helped build planets and, in doing so, helped build everything that came after. They may be faint and far, but they matter. They are the roots beneath the bright garden. They are the deep notes beneath the melody. They are the steady beat beneath the song of the Sunday. Beyond the glow of the familiar planets, beyond the gas giants and their many moons, beyond even the pale shimmer of Pluto's path, the system changes. Sunlight thins, warmth fades. The worlds become fewer and smaller. The loud patterns fall away, and the quiet ones remain. Out there, planets do not roar or glitter. They drift cold, faint, and patient. These are the forgotten worlds. They belong as much as any giant close in. Across this journey, we have crossed their domain. We paused over Ceres, circling between Mars and Jupiter, marked by bright salt and hints of brine below. We skimmed Haumea, the spinning ellipse with an icy sheen and a narrow ring. We passed Mike, red and reserved. We noted Eris, whose discovery forced us to rewrite our labels. We tracked Sedna far in the dark on its immense orbit. We watched Orcus keep time with Neptune, a quiet mirror. We looked down on Quawa and its thin ring. We noted Gongong's deep red. We nodded to Salacia, Varuna, Ixion, and many more small sparks on a wide sea. We walked the slow gravel of the Kuiper Belt, wandered the tilted paths of the scattered disk, and stood at the threshold of the Oort cloud, where the sun is only another star. These are not worlds of spectacle. Most are too small for naked eyes, too distant for warmth, too faint for easy pictures. That is why their beauty works the way it does. It is quiet and it feels old. They have held their places almost unchanged since the beginning. Inside their ice lies the raw material from which the brighter worlds rose. They are the foundation under the towers. We often overlook the quiet. Our eyes go to flashes and flares. We celebrate big rings, deep storms, and bright comets, small worlds at the edge rarely enter the spotlight. They show up as dots and footnotes, names half learned. Turning toward them is like stepping out of noise into still air. It feels like standing in new snow while the world pauses. Seen like that, they become what they are, not scraps, but survivors. They endured the chaos of youth. They saw the giants migrate and settle. They watched the inner worlds cool and host seas. They marked the first comets and the first rains. They kept the water and organics that later fed oceans and air. Every river and tree can trace part of its story back to those cold carriers. The edge is not decorative, it is structural. Their pace offers comfort. On Earth, days fly and years blur. Out beyond Neptune, time stretches. Sedna needs millennia for a single loop. Bodies in the outer cloud may not have circled once since humans first stood upright. Their clock is the clock of mountain ranges and drifting stars. Not all meaning is fast. Some meaning is built by patience. They are not trying to be noticed. They are not waiting for praise. They circle, century by century, constant and calm. They are content to be quiet. That may be their lesson. Beauty is not always loud. Significance is not always bright. Some wonders ask us to be still. One day, we may pass them with our machines. Small eyes on small frames may drift over their plains and ridges. Images may come back as soft reds from tholins, faint glints of buried ice, clean shadows of ancient craters. Even if we never go, they will remain what they are, turning in long night. They do not need us to be real. They do not need names to endure. As you let them recede in your mind, the inner planets glow ahead, and the small outer sparks grow faint like embers on dark cloth. They do not fade because they lack worth. They fade because distance softens all things, and distance is what they know best. They are not gone. They are simply returning to their silence. Leave them that way. No grand ending. No applause. Let them be as they have been for ages. Patient, still, and sure. Let them turn in their far darkness while you keep their quiet light. The solar system holds loud, brilliant worlds, and also soft, cold, nearly forgotten ones. Often, it is the ones no one notices that teach the most. So let the noise fall off for a moment. Picture stars in every direction. Picture the sun as a pin of light. Picture the small worlds circling in silence, just as they did at the beginning. You drift by, weightless and unhurried, moving on, but not really leaving. They remain. They always will. The lights dim. The path bends inward. The forgotten worlds keep turning in the dark, and you are gently, quietly on your way home.